Hello, this is the next video in a playlist that I'm calling Applied Multivariate Analysis. And we're in Chapter 7, part of this playlist, which I'm calling Classification Analysis. And let's jump to today's topic, which is K nearest neighbors classification. So here's the setting. Assume we have n observations with p variables per observation, so they're vectors that have been previously classified into M groups, G1 through Gm. We wish to classify one observation Y with p variables, an unknown assigned group, into one of the M known groups. And K nearest neighbors classification is this. It's essentially we have these n vectors in space, p dimensional space. And then we plot the next observation in p-dimensional space, and we see what data is closest to, and then we assign it to that group. I mean, it seems so simple. It's the earliest non-parametric classification method by Fix and Hodges in 1951. So to do it, we classify an observation. To classify an observation vector Y, we compute the statistical distance from Y to all other n observations. And that's what DJ squared is. It's the statistical distance from our new observation vector or to all n other vectors. And it's statistical distance, so we're adjusting by the pooled sample covariance matrix. And then we look at K points nearest to Y. And then we count how many are in each group. So K1 is the number the number in group 1. So we look at K points, and K1 is how many are in group 1. K2 is how many in group 2, all the way to Km. Now K, of course, has to be the sum of these Ki's, right? Because that's how many points we looked at. And then we assign Y to group I that has the highest proportion, Ki divided by Ni, among the K nearest neighbors. And that's it. So it's recommended to use a K. So what do we use? 3, 4, 5, 10. We use a K that's roughly the square root of the average typical group size. Now, one note here is that most functions in R use Euclidean distance as opposed to statistical distance. And we'll look at those in this example here. Now, this is the example we've used in the previous 2-3 videos, so we can compare the results from each method. So the data is from an FTP site listed here, and the file name is t617fish.dat. Now it's by Baden, Tack, and Bader in 1958 compared judge scores of fish prepared by 3 methods. 12 fish were cooked by each method, and several judges tasted fish samples and rated each on 4 variables. Each entry is the average score for the judges on that fish. So the 4 variables are aroma, flavor, texture, and moisture. Now let's fire up R and analyze this. So first we read the data. I guess technically first we load the library called class, and that's short for classification. So it has a bunch of built-in classification methods in it. Now the data doesn't have variable names, so we assign names to the columns, so method, aroma, flavor, texture, moisture, and I make the group, which is column 1, a factor, which kind of helps in some of the statistical calculations, which I may cover later. We print out the first 6 observations using head. We calculate the sample size in each group and store it to n. We calculate the pooled covariance matrix. And as always, the R code will be copied and pasted into the comment section, so you can copy and paste it into your R program and rerun it. Now, I create a function here, which I'm not necessarily recommending that you use, but more of just illustration of what's going on. I call it KNN, which is K nearest neighbors. We have group, our existing data, the new observation, the covariance matrix used, and what K, what size. And so the group and the sample size for each, we have the Mahalanovas distance, which is the statistical distance from all the data to the new observation using the variance covariance matrix. Now this next one, I sort them, but I only sort the first K, which is so much more efficient than sorting the whole vector and then finding the first K. So this one scales so much better. If you're only sorting 50 to 100 each time, it's not going to matter. But if you're going to sort 100,000, this is going to save a tremendous amount of time to only sort the first K. So then I want to know where in the observation vector did these come from, and that's where I find the index with this, and then I have to find which group, and we calculate the Ki over n, and then we want the largest of those. That's what the which max finds. Okay, so now let's illustrate these. So let's let K equal 3, so the 3 nearest observations to this next observation, and then we'll assign it based on those 3 observations. So I put it in K, capital N, capital N. So Yn is our group. This is our data. It's the remaining columns, not the first. Next Y, of course, is this pooled covariance matrix, and K is 3. And it would assign it to group 3. Now, if we use the built-in function, K little n, K nearest neighbors, it also assigns it to group 3. Let's do one more. Let's take the 14th observation from our data matrix and see where it would be classified. So using my little function that uses the statistical distance, it would classify it as group 2. We use the built-in function and it classifies it as group 1. Now remember the difference, well, there's a couple differences. One is the built-in function uses Euclidean distance, not statistical distance, and my function uses statistical distance. And another subtlety, which I'll point out in just a second, is if there's a tie, so the group 1 and 2 each, have, an observation. Well, when K equals 3, so all of them are tied. So we're near each one of them. My function just grabs the first one and then reports it. So it's going to over-report, the smallest group number. Where KNN, the built-in function, would then, when there's ties, it randomly assigns it to one of the groups. Okay, and to illustrate that, let's do this. So let's let K equal 5, and we're going to take the data matrix Y, remove one, and then classify it again using each of these methods, statistical distance and the Euclidean distance from built-in function, right, to see how well each one does. And so that's what this function does. So the predicted K, capital N is my little silly function, little n is the built-in function. And then we plot my predictions, I say the statistical distance predictions against the actual, and that's what this is. So it looks like it misclassifies 14 observations. And then let's see, the built-in function misclassifies 9, 10, 13. So one does one better. Now, where are we differing? So if we look at the built-in function versus the statistical distance function, this is where they differ. I'm not going to review that, just to show you that they do differ. Now, here's what's interesting. So we ran the built-in function once, and these are the results. And now we're going to run the built-in function again on the exact same data, where mine would reclassify it exactly as it did before. But this new function on ties, it randomly assigns. And so you can see that these two tables are different, because the little knn, when there's ties, it randomly picks a group. So you can see that it's randomly picked different groups this time than from the previous time. Okay, so we're at 10 minutes. I'm going to stop here. Hopefully you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.